Today we will start the theory of limit of functions, and we will learn the entirety of limit of functions, and then in the next class we'll be going on to the continuity of functions.
Hello, guys. Welcome to Cheenta School of Statistics and Data Science. To book a trial class for your preparation courses of IIT MS, ISI MStat and CMI MStat Data Science, check out the first link in the description below. If you're enjoying the video, show some love by liking the video and subscribing to the channel. We welcome you again to this passionate community of budding statisticians and data scientists. Let's enjoy the rest of the video. Stay tuned and stay blessed.
So, what about the limit of functions? Why is that you have understood that limit of sequences? What does limit mean? But the basic idea of limit of functions, you have got this idea of limits from college only, from your schools. You have learned a bit of limits in your high school because it was there in your 11th, 12th. But today, or in this class, we will learn about in the depth of it, like what do actually limit mean? Uh, what happens when a limit doesn't exist of a function? So the idea of limit of a function is similar to the idea of limit of a sequence when x tends to infinity. But what about when happens when a limit exists towards a point? So I remember, I had a hard time understanding the concept of limit in high school because I could understand how it's different from, the value of a function. So limit of a function. So let's say if I take this limit x tends to 2, x square minus 4 by x minus 2. Okay. So if you observe that for x not equal to 2, this, so as you can understand that you can do it like this, the limit x is equal to x plus 2. You can cancel it out, rationalize it, okay? In this manner, you can find that the limit is equal to 4. But I had a hard time understanding that, why it is that at x is equal to 2, it doesn't, take the value. So the basic idea is that if you draw this graph of this function, so at 2, so what will happen is that the graph of this function will be x plus 2 only. So at 2, so it will be like this only. But since at 2 it's not defined, there will be a small gap here at 2. The rest will be all defined similarly. The question is that even if there is a gap, the idea is that this function is going towards this value 4. So how to define it, that it's going towards this value 4, but it's not taking the value 4. Since x equal to 2 is not defined, this will be undefined here. So this function is nothing but x plus 2 if x not equal to 2, and undefined otherwise, undefined if x is equal to 2. So the question is that even if the function is not defined at this point, how to make sense of the limit? That's the basic idea. So this tells you that the limit is nothing but where the functional values are approaching. So the question I had is that how is limit different from that point value? Okay. So the issue is that at that point the function may not exist, but the other values on all the sides, it can go towards that point. You can go towards that value. How do you mathematically define it? So in high school we have learned a lot of techniques, but we didn't understand what's exactly going on, like how do we define it mathematically. So therefore in this class today we will be learning about the following things. So we're learning about the limit definition, and we'll see epsilon delta and the similar approach to that coming up. We'll apply it in a few examples. So let's go to the limit definition using epsilon delta. So limit definition using epsilon delta is I am assuming that fx is tending to a limit L. Fx is a function. So what do we mean in this case? Well, like what exactly is meant here when we say that fx is going towards a limit L? So the meaning is very simple. It tells you that the idea is this, basically this, that let's take this example again. So observe that the limit, the function at that point as x tends to c. The function at that point, let's say c, may not exist. The functional value may not exist. Okay. So you have to just check using the definition when, yeah, the functional value may not exist during that point. Okay. So just remember that. So it tells you that the basic idea is that when x will tend towards this value, the fx will also tends towards this value. That's the basic idea of limit. Okay, when x is tending towards certain value, the fx is also tending towards certain value. So that's the basic idea. Towards the value means the limit value. Okay, so if I give another example, let's say in this case, let's take this case, and the at point value at point c is this. Here observe that the limit is this, not this red point. So the function is defined like this, and observe that the limit is this black point, black value, not the red value here. Although the function value at that point is that. Okay. So we will check with terms of L. Okay, that's it. So remember that when x is around that c, remember that. So this is very important. So let's get started. Let's get started. So the basic idea is that as x is around or near c, fx should also be around L, the limit value. Okay. So this is the basic idea. As x is around c, fx is also around L. Okay. In sequence is as x is going to infinity, fx is around, the fn of was around L, around that value, limit value. Okay. That was the definition of sequence. Similarly, like this, as x is around near c, fx is also around L. So when in sequences, if you remember that as n was around infinity, n was around infinity, but there is only one way to go to infinity. That's as n is greater than certain value, a big value. For all value, f of n should be around L. That was the idea of sequential behavior. So around infinity means around, or like it's after a certain value. Okay, after a certain value. So this is the basic idea. So how do you implement this? The definition is this, that the definition of this is this, that for all epsilon, so essentially you fix first epsilon. Okay, and then it happens for all epsilon. For all epsilon, it tells you that there exists a delta. So these are two, epsilon and delta are two things to measure the closeness of the x near c and fx near fc. Okay, fx near fl, fx near L. I'm sorry. Okay, so such that whenever mod fx, sorry, x minus c is less than delta and greater than 0. Remember that greater than 0 is so important out here, because it's not taking the value c. Remember that, because once it takes the value c, it will not be limit, because the fx and fl is not around that point. Remember that the fl and the fc is not around that point. Sorry. So we cannot take the value at c. We just take if x minus c greater than mod is greater than 0. That means because at c it may not be, the limit is different from the value at c. That's why. So as x is near c, not equal to c, near c. Remember that. That is very important. Near c or around c, then whenever this happens, then the fx should be around L. Sorry, around epsilon. That means yes. So that's the basic idea. So you can say this is telling you the closeness around c, and whenever that happens, fx should be around L. So also you can understand that as x, so this is equivalent to saying that as x is less than c plus delta and greater than c minus delta. Sorry, where x is not equal to c. Is this right? And x is not equal to c. Remember that, with the condition that x is not equal to c, because equal to is not there. And here it means that fx is less than L plus epsilon and greater than L minus epsilon. So if this condition holds, so it's like it's fixing a value, it's checking a value around this fx, it's taking a strip around this fx, epsilon epsilon strip. So this is L, this is L plus epsilon and L minus epsilon. For this, it's telling that if the limit exists, there exists a delta around this value, there exists a delta such that whenever this x is between this delta, okay, the values around this region, the fx, the values taken in this region is between this L and L minus epsilon and L plus epsilon. So as epsilon changes, the delta should change. Probably as epsilon goes to 0, as epsilon decreases to 0, delta should also decrease to 0. That's the basic idea. Let me show you some animation now. It will make you more clear. So it's telling you that as let me just check this function out. It's a continuous function. That's a different thing. But it's telling you that understand as fx is near L plus epsilon. Okay, here epsilon. Let's take epsilon to be 2 here 2. So let's take epsilon this big. For this epsilon, observe that for this epsilon, observe that the delta should be around this. Yes. And epsilon as increases, the delta is around this. So the green region is that this delta is good. The delta lesser than this is good, but delta as it goes more than that. For example, when delta goes here, observe that at this point it's outside the range. Essentially, what it means that in this rectangle, the graph will always lie. In this rectangle, observe that the graph doesn't always lie. Okay, in the entire thing. In this rectangle, observe that in the rectangle, the entire graph lies so that it starts from the left hand side, left hand bar to the right hand bar. That means whatever the values it's taken in this delta region, it's inside this epsilon dash. So for it should happen for every epsilon. So if you decrease the epsilon even more, can we decrease epsilon even more? Yeah. If you decrease the epsilon even more, it means that whatever the values it's taken in this epsilon L plus epsilon, this region, there exists a delta such that all the values in this C plus delta and C minus delta region, C plus delta and C minus delta region, it should lie inside this. Okay. All the values, so there exists a C minus delta, C plus delta, sorry, a C plus delta region without the C value, which lies inside this hole, like all the values should lie inside this. The values will lie inside this L minus epsilon plus L plus epsilon region. Did you understand?